Hi everyone, so this is Unit 2, Atomic Theory. We're going to learn about the evolution of the atom and the configuration of an atom and all the parts of an atom. So the vocabulary is on the first page, excuse me, and you will have a vocabulary quiz at some point next week, and you will access Quizlet to go through the definitions and quiz yourself before our in-class quiz next week. So let's go through our objectives for today. As you can see, the vocabulary continues over here. Kernel electrons, valence electrons, cations, so on. These will all be on Quizlet.com, and I will explain that in class. So the objectives we are going to cover just for this lesson will be to understand that the modern model of the atom has evolved over a long period of time through the work of many scientists. And we will discuss the evolution of the atomic model. All right, so the evolution of the atomic model. The atom is the basic building block of all matter. This is really sloppy. And we also now know, after we talked about simple substances, cannot be broken down. These are elements. Okay, atoms make up the element. So we cannot break these down chemically or even physically, for that matter. Democritus would be the first philosopher, Greek philosopher, to have answered a question about what matter is made up of. So Democritus was about 450 BC, which is before time really began. And he was Greek, a Greek man, who tried to answer all of these questions about matter and about the divisibility of matter, if it can actually be split. So he tried to answer the questions I'm going to try to squeeze this in here, about divisibility, right? Divisibility of matter. And he used the term atomos. Okay, atomos, which is Greek for indivisible, all right, or the ultimate smallest particle of matter. All right, so Dalton came around 1803, so there was a huge gap in time here, and Dalton, around 1803, known as the founder of the atomic theory. So as time went on, the former scientists kind of put it to the side, really couldn't find an answer to everything that we were looking for. So Dalton invented the word atom as the basic unit of matter, which were considered to be indivisible. Indivisible, meaning we can't break it down. Dalton also claimed that all atoms of a given element are identical, making it a pure substance, just as we learned in Unit 1. He also discovered that atoms of different elements have different properties and masses, and we're also going to learn later on this is how they are arranged in the periodic table by mass and their properties. So he also found that combining atoms of different elements formed compounds. And the theory was referred to as the cannonball theory. It looked like a simple sphere. What does this name tell you about Dalton's atom? Well, it's probably going to look like a cannonball. So really his idea was that this was an atom right here, nothing else. Indivisible, not made up of anything else, just a round ball or a sphere. The next scientist, J.J. Thomson, 1897, so we're talking about, about 94 years later, while using a cathode ray tube, he discovered that the ray was deflected due to a magnetic electrical field. From the discovery, he concluded that atoms contained some small negatively charged particles called electrons. And the symbol for electrons is E with a negative sign, meaning negatively charged. All right. The theory famously referred to as the plum pudding model, because he visualized that the electrons were embedded within the structure. Within the structure of the atom, just like raisin bread. So he kind of just said this, here's the atom, and then there were these negatively charged particles spread throughout the atom. The mass of the rest of the atom, besides the electrons, was thought to be evenly distributed and positively charged. So basically what he is claiming, J.J. Thomson, was that this whole atom was a positive charge and these negative charges were embedded in the atom itself. Okay, so here's Rutherford, 1909. So a few years later, the experiment was called the gold foil experiment, and this is very important because they always ask this on the Regents. So it is called the gold foil experiment. And why was it called the gold foil experiment? Well, go figure. It had to do with gold and some aluminum foil. So this is where he bombarded, using a particle accelerator, bombarded a thin piece of gold foil with a positive stream of alpha particles. These alpha particles were obtained from helium, often referred to as the nuclear model. Not nuclear chemistry, we're not talking about nuclear power plants or anything like that. It was just called the nuclear model because he basically discovered that there was a nucleus. Most alpha particles went straight, and they went straight through the foil, and some were deflected, indicating that something was in the way that caused them to bounce back. So two conclusions were made by Rutherford. Most of the atom is empty space. And this is important because this is definitely one of the major conclusions that were made from this experiment. And the atoms have a dense positive central core, or middle central core, called the nucleus. And that's why it is called the nuclear model. So here he basically is stating, here's the atom, and we have something in the middle, and everything else is empty space. So he didn't actually discuss electrons at this point, but that there was something in the middle that was causing these alpha particles, which are positively charged, to bounce back. And the next scientist, Niels Bohr, 1913. So another couple of years later, proposed that the atom consists of a dense nucleus with electrons. So now he combines theories of the previous scientists and says, okay, so we know that electrons exist, we know there's a nucleus, let's put this together, and that they are found in the well-defined orbits or paths. Now in this little image here you can see we have these paths right here, and these would be the electrons, and they are located in specific orbits surrounding the nucleus. He therefore stated that each electron orbiting the nucleus must possess a definite amount of energy to keep it in place within its orbital. This is known as the planetary model. Kind of like how the planets revolve around the sun, they're all in fixed locations, just like our solar system. Okay, so again, everything that I bullet is the important points of the atomic theory and the evolution of the atom. Notice as we go on that we're getting more defined and more specific. Finally, the last model, this is the present day model that we have, a little fuzzy image of an atom. It's called the wave mechanical, or the cloud model. Again, modern present day model, developed after the famous discovery that energy is made up of both waves and particles. So there was some quantum physics going on here. Still the same dense, positively charged nucleus. And electrons now have distinct amounts of energy and move in areas called orbitals. Okay. Or, and then we're going to have to write some here, regions around the nucleus where electrons are most likely to be found. Most likely to be found. Okay, again, most likely to be found, because we don't know for sure, but we can kind of make a guess, or this is again on theory, that this is where they should be based on how much energy they have. Many scientists have contributed to this theory, many, and we're not going to list them. Different from the Bohr diagram, okay, now the location of the electron is based on probability within the orbital, and that's why we said most likely. It's a probable location within the electron, the atom, okay? And this is a 3D model, and I will show you some images in class tomorrow on this, and we're also going to continue with pages 4 and 5 of our note packets in class. So we will break it down by date, the scientist, the name of the model, and what the conclusions were from each scientist. Okay, so we are done with lesson number 1.